Okay, hey guys, how you doing? We left off last time on this problem here. This problem wraps up this section, right? On trig substitution. It is something you absolutely are going to have to do over and over again, and especially the struggles I saw last night. I'm here to help you with those. So bring them to me, but bring problems that you've attempted, and let's get through this. Let's get through this. Like I said, this encompasses so many skills. You got the antiderivatives, you got the trig functions, and we're adding integration techniques on top of that. And so there is no substitute to graphite the paper. And let me help you. Now, the next thing we had here, I didn't click to this slide last time. There's a homework for that. All right, so we'll make that due next time. There's a homework for you to do. It is very similar to this one. Here's the answer. Okay, here's the answer. So work toward that answer. And today we're actually going to start section 8.5. 8.5 is the method of partial fractions. What it is a method by which over the real numbers can be factored into sorry, I heard a beep. The computer gave me a beep, so I wanted to see what was happening. Any polynomial can be factored into linear factors, some of them possibly repeated, and irreducible quadratic factors, and some of which could be repeated. So for example, this denominator right here, the first one is a linear factor. And it's repeated. By that meaning it's squared or raised to a power higher than 1. This is a irreducible quadratic factor, with the key being irreducible. Quadratic factor, right? And this is non-repeated in this case. Is less than 0. I think the internet is going in and out here. You may be having some interruptions in this recording. I hope not. But b squared minus 4ac is less than 0 on factors that are irreducible. That means you cannot factor something like this into 2 other factors. You can't take that and factor it into 2 linear factors that are multiplied, right? You can only do that if the discriminant, this is the discriminant, You can only do that if the discriminant is greater than or equal to 0. All right, so know the difference between a reducible and irreducible quadratic. All right, so an irreducible quadratic has a discriminant less than 0. And so you can't factor it into linear factors. So in our procedures, we're going to factor, especially the denominators, we're going to factor into linear factors when possible. The rest of them we're going to leave as irreducible quadratic factors. All right. So what you should walk away from with this slide here is that the method of partial fractions is a way to, it's an algebraic technique to break down, it breaks down, get rid of this. It breaks down this integrand here. This integrand here equals all of this stuff. All right. Now, why do we want to do that even? It's nice that those two are equal, and it turns out they are. In other words, if you added all these together, if you added these rational expressions together, you would get this on the left. Why do we want to do that? Because we know how to integrate these. We know how to integrate these, and we don't know how to integrate that. All right, so the method of partial fractions breaks down a rational integrand that we don't know how to integrate into partial fractions like this. This is called the partial fraction decomposition. Decomposition, that's what this is. Partial fraction decomposition. Each of those we know how to integrate. Some of them are going to be messy, but we know how to integrate them. All right. Bernoulli, very famous scientist, actually. If you have had any natural sciences, you know that about Bernoulli's principle, right? Swiss mathematician, very fundamental, came just after Newton. And he is the one who is given credit for introducing the method of partial fractions. He had many outstanding students, the most famous of whom was Leonhard Euler. And Leonhard Euler might be the most prolific mathematician of all times. He had so many results. A legendary mathematician, Euler is. But Bernoulli stands as one of the greats as well. What's happening here? Okay. This is one of those slides that we're going to understand more after we do it. So I'm not even going to go through that slide right now. There are 4 cases in the method of partial fractions that we are going to consider. We'll only get into 1 or 2 of them today. All right. Case, basically, it depends whether you have linear or irreducible quadratic factors in the denominator, and are those factors repeated or not? Okay. We are going to cover probably case 1 and maybe some of case 2 today. All right. And 3 and 4 will be later. They're more involved. All right. Now let me show you how this works. And I stress that this is an algebraic procedure that we're doing initially. And we're going to break this integrand down into a partial fraction decomposition that we know how to integrate. All right. Now, here's how the procedure works. The procedure works like this, and this is a theorem, actually. Right? This big slide right here, this slide here is a theorem. It's a big, ugly theorem. Okay. Now I'm going to show you how to use it. The theorem says that my integrand here, this is really a 1 in the top, right? 1 over x squared minus x minus 2. So we're going to apply partial fractions over here. And it works like this. 1 over. Now we have to factor the denominator. We have to factor the denominator into linear factors if possible. Now, is this an irreducible quadratic factor? Well, if you're scratching your head, just do the discriminant, b squared minus 4ac. B squared is minus 1 squared, which is 1, minus 4 times a, which is 1, times c, which is minus 2. So 4 times a times c is minus 8. So 1 minus a minus 8 is positive 9. That is positive. So this factors into linear factors. And without too much difficulty, you should be able to get that into what? X, what will it be? Minus 2x plus 1. So it factors into 2 linear factors that are non-repeating. That means each of these are to the first power. Right? If it were just second power, third power, so on, those are repeated factors. So the theorem of partial fractions says that we can take our integrand here, which is 1 over x minus 2 times x plus 1, and that is going to equal some number a over x minus 2 plus some other number b over x plus 1. Now, both of these on the right here, both of these terms, you know how to integrate. A pop quiz would be, how do you integrate these? We're going to see in a minute. All right. It's very straightforward. You should know it. Now, this is what the theorem says. How do we find A and B? That's what we need to find, A and B. So now, must find A and B. And when I find A and B, I'm done with the partial fractions part. Well, let's see. What would I get if I added these two? I would get A. Now, this first term, our common denominator is going to be x minus 2, x plus 1. So to get that common denominator on the first term, I got to multiply top and bottom by x plus 1. Oh, don't tell me. It's already frozen on me. What happened there? All right. This computer is acting funky today. All right, we doing this? That's bad because it basically crashed out on the first slide that I wrote on, really. Almost the first slide, second slide. Computer is very slow. Come on. If this continues, I'm going to close out this video, reboot the computer, and start a second video. Yeah, it lost everything, so we go over here. All right, let's try that. All right, as I was saying, if you were going to add these two fractions at the top right, you need to get a common denominator of x minus 2, x plus 1. And just for safety, I'm going to save this. Okay. You need to get a common denominator of x minus 2, x plus 1. So this first term, we'll need an x plus 1 on the top and bottom. So you have a times x plus 1 on the top, plus b. The second term is going to need an x minus 2 on top and bottom. All right? Now notice that equals what's on the left. And our theorem says numbers a and b exist so as to make this true. So now you notice that you have the same denominators. So if the denominators are the same, then so are the numerators. So we're going to take the numerators and set 1 equal. That's the numerator on the left. And this is going to be right here, the numerator on the right. Okay. All right. Now, being the creative genius I am, I'm going to call this the left-hand side, and I'm going to call this the right-hand side. Now, watch what we do. Multiply things out. All I did is multiplied through by a and b. And we're going to regroup. What are my coefficients for x? So over here on the right-hand side, I have ax and bx. So that's a plus b times x. What do I have left over? For a constant term, I have a minus 2b. And on the right, that still equals 1. Excuse me, on the left, that still equals 1. All right? So, any questions? Jesus, are you listening? Get off your phone. Just writing on your bro. So once we have it in this form, we're going to make a little chart. Okay? we're going to have up here left-hand side, right-hand side. And really, we have two things. I'm going to erase a lot of this. I do them too long. I have two things. We have x's and we have constants. I'm going to call them c's, constants. Okay? Question. How many x's do I have on the left-hand side? Answer. 0. I just have a 1 there, right? No x's. How many x's do I have on the right-hand side? I have a plus b. That means, maybe I'll do this. That means that a plus b has to equal 0. Right? The number of x's on the left, 0, has to equal the number of x's on the right, which is a plus b. Constants. How many constants do I have on the left? I have the number 1. How many constants do I have on the right? A minus 2b. That tells us that a minus 2b equals 1. The coefficients, the constants on the left, 1, has to equal the constants on the right. So here, in this, we have a simple system, in this case, simple system, of 2 equations and 2 unknowns. And so we can solve that for A and B. We can solve that for A and B. So from this right here, I get A. Oops. A is negative B. And so plug that in down here. Negative B minus 2B is 1. Minus 3B is 1. That tells me B equals minus 1/3. Right? So A equals negative B. Remember that from up here. A equals negative B. And that is going to be the negative of negative 1/3 or 1/3. So A equals 1/3, B equals minus 1/3. Right? That means, so, that means 1 over x squared minus x plus minus 2. That is 1 over x plus 1, x minus 2. That equals my A. What's my A? 1/3 over x plus 1 plus B minus 1/3 over x minus 2. This is what we were after right here. And this right here is the partial fraction decomposition. How does that help us? Well, we're going to take this. This is going to go all the way back up here. So our original integral now equals the integral of 1/3 brackets 1 over x minus 2. And it froze again. My board froze again after only 10 minutes. All right, I'm going to close out this video and I'm going to reboot the computer. So there will be 2 videos for today. I'm very sorry we had to do this, but I checked the next video.